Hi, good afternoon. Welcome to Embedded ETESTCON, a Menlopark initiative. This is Sahana, Software Quality Engineer at Menlopark Technologies. Menlopark Technologies is a leading provider of embedded hardware and software products to automotive, automation and aerospace industries across the globe. Our engineers can advise you on the best product set to suit your technical and business needs, and we offer product configuration and bundling of hardware and software solutions for hassle-free product development. Moving forward to the next presentation, we now have with us Mr. Johan KRAFT, who will share us the insights on software quality assurance with Visual Trace Diagnostics. The presenter for current session, Dr. Johan KRAFT, is CEO and founder of Percepio. Dr. KRAFT holds a PhD in computer science and is the original developer of Percepio's Tracealyzer tool for Visual Trace Diagnostics.
Hello everybody. In this presentation, you will learn about the challenges of system-level software testing. You will learn how secure connectivity can provide an additional remedy for IoT quality assurance using Percepio DevAlert that allows for increased product sales, reduced liability risks, and lower costs. My name is Johan KRAFT, and I'm the founder, CEO, and CTO of Percepio, a company based in Sweden. I have a technical background, PhD in computer science, and my specialty is software tracing, analysis, and visualization of embedded RTOS-based software systems. Let's begin with an outline of the presentation. We begin with motivations, the challenges of system-level testing, and introduces a new remedy targeting IoT devices, our new cloud solution, Percepio DevAlert. This provides monitoring of deployed IoT devices with a focus on the software behavior and also remote diagnostics using our related product Tracealyzer. Tracealyzer is integrated in DevAlert and will be mentioned briefly in this part. But Tracealyzer is also a standalone product for the development phase, which is the topic for the last part of the presentation. A famous quote from Edgar Dijkstra, one of the most respected pioneers in computer science, is that testing only shows the presence, not the absence of bugs. This means that to be certain you have found all the bugs, you need to test every possible scenario and code path. This is rarely possible in practice. According to research presented by the embedded guru Jack Gansel, the typical defect removal rate for embedded software is about 95%. So 5% of the bugs actually remain in the shipped product. This research also shows that the defect introduction rate, the amount of bugs introduced during development, is somewhere between 50 to 100 bugs per 1,000 lines of shipped code. While some might be harmless, around 20% are classified as major defects according to this research. Assuming 5% of these are missed and you have 50,000 lines of code in your project, it will mean that you have somewhere between 25 to 50 major defects remaining in the shipped product that hits your customers. You may wonder, can it really be this bad? Your product seems to work just fine, right? Well, it could be, but the bugs that are missed by testing are typically elusive problems that don't show up right away for everyone. Otherwise, they would not have been missed, right? The bugs typically depend on specific circumstances that can be really difficult to predict and to cover by traditional testing. While system testing is not the only way of verifying a software system, it is certainly the most obvious and common method. After having tested each part separately in unit testing, applied other verification methods like code reviews and static analysis, you finally test the full integrated system using test cases based on the system requirements. Some issues can only be captured in full system testing, and the effectiveness of system testing depends greatly on how close your test cases reflect the real-world usage of your product. Depending on how well designed and how complex your software is, the number of software behaviors that are possible in real-world usage can actually be an astronomical number, far larger than what can be tested in practice. So even if you think you do tons of testing and you don't find any more issues, chances are that you're nowhere near of finding them all. there might be many bugs remaining, and your customer might then have a very different picture of the reliability, performance, and user experience of your product. So how do we deal with these real-world issues that affect the customers and users? Well, we don't really do it. End users have problems with their devices all the time, and the developers are largely unaware. Customer support might receive complaints and returns, but it's not always clear if the cause is a software issue, a hardware issue, or simply that the user didn't understand how to use the product. Moreover, the users are often not able to provide detailed information regarding the circumstances of the issue, so the developers have very limited means of reproducing the problem. But what if you could capture these real-world issues automatically in a systematic way and get detailed diagnostics on every occurrence? With secure IoT connectivity, this is actually possible by using our new cloud service, Percepio DevAlert. DevAlert provides real-world feedback, allowing for rapid, continuous improvement of the device software. This is likely to improve product sales, as you can catch and fix those remaining bugs quickly after the very first occurrence, before most of the users even have noticed any problem. Higher average quality means higher customer satisfaction, meaning better product reviews and more loyal customers. Improved reliability reduces not only liability risks, but also the costs for customer support, returns, and debugging of customer issues. The provided diagnostics makes it far easier for developers to reproduce customer issues, since they get information directly from the device automatically and don't have to rely on the users to describe the circumstances. Feedback on real-world product performance allows for improving key performance metrics and the overall user experience, so you can make a great product that beats the competition. So what is DevAlert really? It's a cloud-based solution for IoT device monitoring, focusing on the actual software on the devices. This makes it easy for device developers to report any error, warning, or other event of interest during runtime from the devices back to the developer team. This can be used both during testing and in deployed customer operation. By having this in deployment, you will know about real-world issues within seconds after the very first occurrence, instead of having to wait for weeks or even months before some users bothers to report the problem. By having DevAlert enabled during testing, you ensure that issues that are encountered by testers are captured systematically and in full detail and are provided to the developers immediately. So this is really a cloud-connected flight recorder in your embedded software. When an issue has been reported, your development team can then analyze the issue with visual trace diagnostics to understand the problem and the specific circumstances where it happened, which speeds up resolution tremendously. This awareness of real-world issues and the provided diagnostics means that you can take full advantage of over-the-air updates to achieve rapid continuous improvement. This is the DevAlert dashboard that provides an easy overview over recent issues. By issue, we mean all alerts that are of the same alert type and have the same symptoms. For instance, the alert type might be malloc failed, meaning that the system has run out of heap memory, while the symptom could identify the location in the code where it happened or how much memory you tried to allocate. The developer can define their own alert types and symptoms as needed. Alerts also include software traces, and these are directly accessible from the dashboard. Just click the links and the trace file is downloaded. This is intended for visual trace diagnostics in Percepio Tracealyzer, a tool we have refined since 2004. This contains over 30 interactive views showing both overviews and details from different perspectives. This is integrated in DevAlert, but it's also a standalone tool for lab use. The data flow starts in the device source code, where developers add alerts at strategic locations, such as existing error handling code and hard fault exception handlers. When an alert is uploaded, a snapshot of this trace buffer is also included. Since this is a ring buffer, you automatically get the most recent events that preceded the alert. and that most likely can explain the problem. This data is then uploaded to the normal cloud account of the IoT device, just like any other application data, and with the same level of security. Once the alert data reaches the developer account, the upper part, that is the alert signature, is then forwarded to the DevAlert cloud service. This is a fully managed cloud service provided by Percepio, but the trace data is not forwarded to the DevAlert cloud service. It remains on the device developer side at all times. When the DevAlert cloud service gets the alert signature, it is compared with previous alerts from the entire device fleet and classified into unique issues. Notifications are sent to the device developers, but only when a new issue is detected, not for each and every alert. This way we avoid flooding the developer's inbox if the same issue would occur in many devices. Once notified, the developer then opens the DevAlert dashboard to overview the recently reported issues. Finally, the developers can use Tracealyzer to analyze the provided traces. You will learn more about Tracealyzer soon in the live demo. So, how are the alerts generated in the code? Here is an example where a FreeRTOS error handler has been extended with an alert. We begin by storing a user event in the trace buffer. This is a convenient way to highlight the alert in the trace and provide greater means for additional diagnostics, as you can store formatted strings and values much like a printf call. Then we stop the trace recorder momentarily, since we don't want any changes in the trace buffer while reading it. Next, we compose the actual alert, the data package, by setting the alert type and provide additional diagnostic information as symptoms. You may add your own alert types and symptoms as needed. Finally, we upload the alert and resume the tracing in case another problem would occur. This code is from our upcoming demo on using DevAlert on the Cypress PSOC64 secure microcontroller. This demo is a slightly modified version of the official Cypress AWS demo. It runs FreeRTOS and connects securely to AWS IoT Core or Wi-Fi. A USB connection is used for power, device programming, and also provides a serial port for diagnostic messages. We have added the DevAlert firmware monitor and a few demo bugs that cause errors when pushing the buttons. The error handling code then calls the DevAlert API to generate alerts. The source code of this demo is available on github.com/percepio. Okay, so here is the DevAlert dashboard shown in Tracealyzer, and here is the serial terminal to the device. Each row here represents an issue. All alerts with the same alert type and symptoms. We can actually see the symptoms by hovering the mouse like this. Now I push the button on the board and an error is triggered. In the terminal window, we can see a demo message about an assert that failed. The assert macro has been modified to trigger an alert. The dashboard now shows the alert. The red color is used for recently reported issues within the last minutes. But before we look at the trace, we have two more issues lined up. Two other bugs. Let's try them too. I push the button again. Now we got a malloc failed. And one more time. And the board actually restarts here. And that's because the error triggered a hard fault, a division by 0. We generated an alert in this exception handler, but we didn't upload it directly because the device needed to be restarted before an upload was possible. The data was instead stored to internal flash. And then after the restart, when the DevAlert firmware monitor is initialized again, it finds this data in the flash and then uploads it directly. And it should appear here any moment. Let's have a look at this division by 0 error, for instance. The trace data is now downloaded from AWS and is parsed by Tracealyzer. The left view shows a scheduling trace, a timeline of the FreeRTOS task scheduling and interrupts. And we can see a lot more details if we zoom in a bit. Like this. Now we see things like API calls and internal kernel events. This view, the event log, shows all the data as a plain list of events. This is the most detailed view in a way. As you can see, there's quite a lot of information here. But thanks to the efficient encoding, this took less than 7 kilobytes of RAM actually. And it would probably be sufficient with a much shorter trace, say 3 kilobytes or 5 kilobytes. To make sense of this data, Tracealyzer provides a lot of different views to provide better overview. For instance, in the CPU load graph here in the upper right corner, this has a horizontal timeline, and we can see that this task 6, is using about 90% of the CPU time during this recording. Perhaps that's part of the problem, we'll see. The communication flow graph is another type of overview that shows how the tasks are interacting in runtime via RTOS objects like queues and semaphores. And this is actually generated from the trace data as well. We can even click on these nodes to find the corresponding events. Like this, here are all the events on this particular message queue, all the sends and receives. And we can find them in the trace like that. To find a particular event, like our alert message, we can filter the event log like this. We enter a few characters like alert and find our alert message. If we double click it, we find it in the trace. These yellow labels are what we call user events that were added just before uploading the alert. This way we can add any diagnostic information to facilitate debugging, much like a printf. Here we can, for instance, see the address in the program code that triggered the hard fault, and also register values corresponding to function arguments. If the problem is not obvious from this information alone, you can find more clues earlier in the trace data. For instance, we see several API calls here like xqsend, malloc, etc. just before the alert. That tells what's going on, kind of a fingerprint of the software behavior, the context of the problem. This makes it far easier to reproduce the problem for more detailed analysis in a source code debugger. These are just a few examples of the capabilities of Tracealyzer. There are over 30 interactive views of the runtime behavior. This is also available as a standalone tool for general use during development and testing. In the standalone Tracealyzer product, the data is transferred directly using a debug probe or a functional I/O interface such as Ethernet, USB, or perhaps a Wi-Fi connection over the local network. Tracealyzer also allows for continuous streaming, so you can record really long traces if needed, but this is not intended for DevAlert and deployed fleets of devices. That's more of a lab tool. Since the tracing is done in software, this has some performance cost, but it's not too bad. The RAM usage is mainly the trace buffer, and that can be configured to almost any size. In our demos, we typically use a buffer between 5 to 10 kilobytes. This allows for storing thousands of events since the encoding is very memory optimized. The code for the trace recorder needs about 10 to 20 kilobytes of flash, depending on what features you include and what optimization setting you are using in your compiler. The CPU usage is, however, a more complicated matter, since this depends on the event rate, which depends on the specific application code, and how much extra logging you have added. However, the time needed to store an event is measured in microseconds. They are about 100 times faster than a printf over a serial port. The event rate is typically a few thousand events per second, which translates into a processing overhead of a few percent or so. This is a measurable impact, but it's not really noticeable in practice. Note that there is no probe effect in this approach. By this probe effect, I mean the potential change in software behavior from adding or removing instrumentation code. By accepting the monitoring as an integrated part of the system that is always on, the probe effect is no longer an issue. The provided feedback from DevAlert, both regarding bugs and performance issues, can reveal many ways to improve the software, and this could actually more than compensate for the runtime overhead. DevAlert is a subscription service offered to product organizations. There are different tiers for different phases of development, and we can offer single-tenant deployments if needed. We're also working on an on-prem solution during next year for those that can't use a public cloud solution. We have a free 90-day evaluation that you can apply for on our website. Okay, you have seen a bit about Tracealyzer. This is also a standalone product for use during development, and now we'll learn a bit more about that. Tracealyzer provides visual trace diagnostics for developers of RTOS and Linux-based embedded systems. This allows for recording and visualizing the software at runtime. For multitasking embedded software, the source code does not give the full picture of the runtime system, which can be seen like a black box or the dark side of the code, if you will. Visual trace diagnostics gives you a detailed timeline of the runtime system and a large set of visual overviews, metrics, and statistics. This makes it far easier to debug system-level issues, problems that are detected when running the full system, which otherwise can be quite difficult and time-consuming to resolve. Moreover, you can also find software design flaws as early as possible, and thereby improve reliability, performance, and reduce the risk of future problems. Finally, it makes it easy to measure timing and performance metrics for verification of real-time requirements and for tracking and optimizing software performance throughout the development. The data collection relies on a software library with very few hardware dependencies, so it works on essentially any processor and doesn't require any extra hardware. It allows for continuous live streaming of trace data from the target system to host, so you can monitor the system over long periods of time. You can even see live animated views of the data. Let me show you what live streaming looks like. Once the initial configuration is done, we just click Start Recording and Tracealyzer begins to receive, process, and visualize the trace data in real time. This application is a PID motor controller, and we can see the control signals in the bottom right view: target position, actual position, and motor torque. These are variables in the code that we are logging with Tracealyzer. On the left, you see the trace view showing the execution of RTOS tasks and interrupts. Once we have recorded the software behavior of interest, we stop the recording and thereby enable all views and features in Tracealyzer for more detailed analysis. As of October 2020, Tracealyzer supports embedded Linux and the following list of real-time operating systems. Streaming is supported for most of these platforms. In other cases, the recorded data is stored in a target-side RAM buffer, what we call snapshot mode. Software tracing is nothing new, but raw trace data is difficult to use in practice. Viewing this in a text editor isn't very helpful. You get large amounts of low-level events, where most are irrelevant repetitions of the same patterns. You can't see the forest for all the trees. To really benefit from software trace data in everyday development, the solution needs two more components. The data needs to be processed into a meaningful model describing how each event affects the system state. This requires the solution to understand all RTOS services that are traced, not just by their name, but what they actually do. The data needs to be visualized to allow quick intuitive comprehension and actionable insights, even for large datasets. The human brain is visual and excellent at pattern recognition, especially at spotting anomalies in repeating patterns. We can leverage that by showing visual overviews from different perspectives, such as graphs over CPU load or task response times. Finally, by connecting the views, we allow for a top-down workflow that is ideal for system-level analysis. Spot anomalies in high-level overviews and drill down to inspect the details. We call this visual trace diagnostics. This is useful for debugging purposes whenever you need a timeline for your software. This is often the case when debugging a full multitasking system, and especially important when the location of the bug isn't obvious from the symptoms, when the issue is difficult to repeat, perhaps it only occurs once in a while for no apparent reason, or when interactive source code debugging can't be used, perhaps since the system can't be halted for debugging, or that you physically can't connect a debug probe. While many still use printf debugging in such cases, visual trace diagnostics is a superior alternative. The logging is much less intrusive, about 100 times faster than a printf over a serial port, which allows for logging much more information, also from the RTOS kernel. And the data is easier to analyze, even for large datasets, thanks to the powerful visualization. This means less debugging time and more time available for customer value creation. And with better ability to solve complicated bugs, you reduce the risk of project delays or having to work 100 hours per week to make the deadline. Finally, better insight during debugging means less guesswork involved, which is likely to improve software quality as the bugs are fixed properly. Here is a basic example of system-level debugging. We have a software system with a shared resource used by different parts of the software. For simplicity, we're using the serial console UART as example of this shared resource, but it could be anything like global data or other hardware interfaces. When testing this system, it usually works fine, but once in a while, the UART output is corrupted. There are two kinds of data written to the UART. For clarity, this is represented by the letters H and L. Normally, we get about 50 bytes of L data and 20 bytes of H data, as can be seen in the upper part of the screen. At one point, the H data seems to come in the middle of the L data, which corrupts the output. So, what's going on here? To analyze this with Tracealyzer, we record a trace of the test case until we see the problem again. In the trace view on the right, you see the RTOS task scheduling and RTOS API calls. These are recorded automatically in supported operating systems. We have also added a user event in the UART driver to capture this in the trace. User events are shown as yellow labels. We see that two different tasks are writing to the UART, so they are probably interfering somehow. But the trace is quite long, so how do we find the location of this error? To find this, we make use of one of the overviews, the actor instance graph. This is shown on the left, displaying the response time of the tasks, which can reveal interference by higher priority tasks. This view can also show other timing metrics of interest. The actor instance graph gives a high-level overview of the trace, currently at a zoom level of 10 seconds. We can directly see an anomaly that could be related to the problem. By double-clicking on this data point, we navigate the trace view to this exact millisecond and can see what happened there. This is what we mean by top-down workflow. In the trace view, we can see that the red task is preempting while the yellow task was writing its data. Apparently, there was no synchronization here to avoid access conflicts like this. We can solve that easily by adding a mutex in the UART driver. Another important use of visual trace diagnostics is to find software design flaws as early as possible. You have probably learned the hard way that designing RTOS-based software is quite challenging. There are best practices in RTOS software design, and these are important to follow. By design flaws, we mean deviations from these best practices. They are not necessarily functional errors, but they may reduce performance and responsiveness, increase the risk of future bugs, and make the system testing less effective. The impact on system testing can be especially problematic as it increases the risk of elusive bugs that leak out into production devices. This may occur if design flaws causes the system behavior to become less deterministic, more random, so to say. For instance, by introducing unpredictable variations in software timing. Complex and chaotic system behavior reduces the testability and may cause race conditions and other problems that may elude detection during the testing. Design flaws are important to find early, otherwise you might find yourself in debugging hell when the application grows, which may require a major redesign of the software. This is much more difficult in later stages of the project. The earlier you can find software design flaws, the fewer changes are required to fix them. With Tracealyzer, you can easily identify design flaws like excessive dependencies between tasks, unsuitable task priorities, and variations in software timing, so you can fix them early and avoid later problems. This is a technical depth where the interest rate can be very costly to neglect. Here is an interesting example we found in Wi-Fi driver code from a major MCU vendor. When applying Tracealyzer to their IoT demo project, we noticed two issues immediately. We were stress testing the solution by sending blocks of about 500 bytes repeatedly over the Wi-Fi connection, but the maximum throughput was only like 23 kilobytes per second. This is really slow for a Wi-Fi connection. In the trace view on the left, we can see that it takes about 20 milliseconds to send each block. Moreover, during this time, the Wi-Fi driver task was running constantly using all available processor time, as you can see on the right. To analyze why the blocks took 20 milliseconds to send, we inserted a few user events in the SPI driver, where the data was sent to the Wi-Fi chip. We could then see that DMA transfers was used for every SPI message. This is efficient for large data transfers, but DMA was also used for the numerous small handshaking messages that was required for each data transfer. As a result, every SPI message took at minimum 2 milliseconds, even if just 2 bytes were sent, which added up to about 20 milliseconds per data package. The solution was to add a condition on the message size, so that DMA is only used for larger messages. Regarding the high CPU load, we noted that the Wi-Fi task didn't suspend while waiting for the SPI transfers to complete. An RTOS task should suspend itself when it's not doing anything useful by calling a suitable RTOS API function. Those are traced by Tracealyzer, but we can't see any such events here in the trace. This is a sure sign of busy waiting, where the task is waiting by executing a loop until a condition is met. This is considered bad practice, as the lower priority tasks are then not able to execute during that time. When digging some more in the code, we found a likely explanation within a few minutes, as seen in the lower box. The solution is to ensure that the Wi-Fi task uses the appropriate RTOS functions to wait in suspended state, instead of using busy waiting loops. In this case, there was even an option available for this, but it wasn't enabled by default. Last but not least, visual trace diagnostics can be used to measure software timing and resource usage. This way, you can verify real-time requirements and keep track of the software performance and resource usage throughout the development project. Tracealyzer provides timing metrics on task instance level, where you get a data point for each execution, each job of a task, such as task execution times, task response time, periodicity, etc. You can also define custom intervals based on user events that you add anywhere in your code, and then see the time between these events. You can even plot this data as shown on the right. And for all these properties, you can see the lowest, highest, and average values for each dataset. The highest and lowest values are also linked to the corresponding locations in the trace, so you can see the explanation behind these extreme values. Tracealyzer can also provide metrics on resource usage, such as the average CPU usage of each task, plots over memory usage, and the amount of data sent over an I/O interface. This way, you can ensure compliance with real-time requirements of your application, keep track of product performance, and find ways of improving it for a more responsive and capable product, improving customer satisfaction and sales. This can also avoid project delays by enabling early detection of any performance issues. In short, Tracealyzer is the leading solution for visual trace diagnostics and provides several important benefits. Easier debugging of system-level issues, finding software design flaws, and verification of timing and performance. This saves time and money by less debugging time, reduces the risk of project delays, improves product reliability and performance, and frees up developer time for important customer value creation. It works on essentially any processor, and no extra hardware is required. Before we conclude, I would like to show you the steps required to set up Tracealyzer with the FreeRTOS using STM32Cube IDE as example. But the same procedure works for any IDE based on Eclipse when using FreeRTOS or MicroCOS 3 or also SafeRTOS. In all three cases, the Tracealyzer support is provided via Percepio's Trace Recorder library. This is provided within the Tracealyzer installation and can be found via the Help menu. The purpose of the Trace Recorder is to record software events either from the RTOS kernel, from the middleware, or from explicit logging in your application code, and then provide this data to the Tracealyzer host application. To use the Trace Recorder, we need to integrate it in the project build, and next I will show you how. So what we have here is a clean basic project with just FreeRTOS and a dummy task that has been generated by STM32CubeMX, the configuration tool. The first step is to copy the recorder code into the project. I'll begin by creating a folder for the recorder code so my project remains nice and organized. I'm just doing a drag and drop here and excluding the stream ports folder. This is only needed when using streaming mode, but today we'll settle for snapshot mode, which is easier to begin with. Now the IDE asks me if I want to copy or link the files. I recommend to copy to avoid that the configuration files are accidentally shared between different projects. Okay, the code has now been copied into the project. Now we need to make some updates in the configuration header file, trcconfig.h. First, remove this line. This is just a reminder to include the processor header file. For ARM Cortex-M devices, this is needed to provide access to the SIMSYS core library. On other architectures, this is not always necessary. In this case, I think the right file is called stm32l4xx.h. Next, we have the hardware port setting. This specifies what hardware-specific definitions that should be used for the timestamping of events. We'll use this port, TRC hardware port ARM Cortex-M, that works for all ARM-based MCUs. Next, we verify that snapshot mode is selected. This means that the data is kept in a circular RAM buffer that you then read out on demand via the debugger. Finally, we need to specify which FreeRTOS version that is used. If you're not sure which FreeRTOS version you're using, check the FreeRTOS source code. The version is stated in the top of each file. The other settings here are mainly filters regarding which events to include in the trace. You can modify these settings to reduce the amount of data, but let's leave them at their default values for now. In the startup code, main.c, we also need to call vTraceEnable with the argument trcstart. And finally, in the FreeRTOS configuration file, freertosconfig.h, there are 2 or 3 more things we need to check. First, we should ensure that config use trace facility is defined and set as 1. Next, it says here that when using STM32CubeMX, we should comment out this line to avoid duplicate definitions of the sysdig handler. This has nothing to do with the trace recorder, but let's do that to avoid any problems. Then, in the end of the file, we need to include the main header file of the recorder, trcrecorder.h. This will add definitions that populates the trace hooks in the FreeRTOS kernel, so they call the recorder library on important events like task switches. If you get problems like these, it can't find the header file, it's because we need to update the list of include paths. So we go to the project settings and add the 2 folders containing header files, config and include. Okay, now it seems to build just fine. Zero errors, zero warnings. Good. So let's start a debug session and try it. We let it run for a few seconds and then halt the execution. We can check that some data has been collected by inspecting the global data structure recorder data pointer. Make sure it's not null and that the fields have reasonable values. To upload the data and view it in Tracealyzer, we use the Percepio plugin. This works with most Eclipse-based IDEs. To install this plugin, visit the Eclipse Marketplace and search for Percepio. Before using it for the first time, open the preferences and make sure that the path to tracealyzer.exe is set correctly and that the right RTOS is chosen. You can then select Save Snapshot Trace and it should load in Tracealyzer. And there you go. To learn more about Percepio Tracealyzer and Percepio DevAlert, visit our website percepio.com. Thank you.
Thank you, Dr. Johan KRAFT, for delivering the insights in today's session. We request all the delegates to drop your questionnaires in the chat box now so that we resolve your queries. For further updates and to know more on the technology and usage of tool, you can write to us at support@menloparktech.com or marketing@menloparktech.com.